what is meant by the tuning method and why the tuning method is required for closed loop simulation. So in this case, there are two documents, which is the slide, the PID controller design and tuning, and of course the exercise to supplement the theory understanding. So in this case, we take a look. Let me give you some briefing, some revisit of the what has been covered before. So here, what we want to do is the closed loop simulation, the closed loop process. Where normally, based on the previous class, the closed loop process can be represented by the use of block diagram. So let's say we have the block diagram, Km, and then we have the comparator, it go to the GC, it go to the GV, it go to the GP, and then we have the summation of your GD coming into the system. Then we have the output before we go back to the GM. And then it return to this one. So you have the plus minus here, plus plus over here, where you have the Y prime S and the input here Y prime SPS. So the Y represent any variable, output variable, or sometimes we call it a control variable. The variable that we want to maintain for any given process, such as temperature, composition, level, or the flow, and so on. So here the typical variable that we want to use is either temperature, composition, or the level. So by here we assume the pressure is under fixed condition, so no need to control the pressure, and the flow mainly used for the manipulated variable. So in the closed loop, why it is called closed loop? Because if you take a look on the diagram, on the closed loop block diagram, you can see there are the loop. So this is the loop where the process starting from the GP and GD, and then it will go back to the comparator where you will compare or we calculate the error between the desired set point value with the measured value. So from this part, if you have a deviation between the set point and the measured value, this means you not achieve the target. So how to make sure you achieve the target? Then you need the controller here. So this is the thing that play an important role, the GC, where here based on the theoretical knowledge, your GC may consist of the three type of controller, which is the P, PI, and PID. So the objective of the controller is to make sure the process variable reach and maintain the value at desired set point. The set point is the value that we want to achieve and maintain. Here, not only achieving the value, but also need to maintain. So that means since we consider our process under dynamic, so the time is changing. So that means as long as the process is operating, the time is also moving. So we need to ensure our control variable, the value for control variable can be maintained at the desired set point value. So this is the thing that we has investigated before, where we use, based on the closed loop, we use the offset calculation. to check how the offset can be obtained. Based on the offset calculation, normally you can calculate y prime SPS minus y prime infinity. So this is the thing, when we calculate the offset, we can see at the final time or at the time equal to infinity, where are your process variable. If you get offset equal to 0, then we can say the controller able to maintain the process at desired value. If you achieve offset not equal to 0, negative offset or positive offset, this means you need to further improve your controller. And based on the last class, we also check the stability, where for the stability, you will use the Roos array method. The main weakness of using our offset calculation is because the value calculated only at final time, at time equal to infinity. Whatever happened in the between, we don't know. So you need to supplement it with the stability analysis to check. In some cases, you may get 0 offset, but the stability indicate that the controller parameter is out of the range of stability range. So this is the thing, is undesirable in the chemical process industry. So that's why for this topic, we need to combine the offset with the stability analysis to check either our controller parameter satisfy the stability range or not. So in this case, normally, based on the previous example, previous tutorial, the controller parameter are given to you. For example, I give you the value Kc equal to 1. So you calculate what is the offset. Kc equal to 10. What is your offset? So meaning that in this case, the Kc has been specified. So this lead to another question. How we can determine this controller parameter other than assumption? Note that every controller, every chemical industry normally has a different dynamic, different profile. Some is fast response, some is a slower response. So this means there are a needs to have the different controller value. Sometimes we just cannot simply assume the controller parameter value. So a suitable method need to be available for giving us the starting point of your controller parameter, which is the Kc, the tau I, and the tau D. So here we take a look on the effect of different Kc value. So for this part, you can see there are different Kc value and the tau I value. So since we have 9 figure in this slide, you can see you have the Kc equal to 5, Kc equal to 3, Kc equal to 1 on the left. On the top is tau I equal to 5, tau I equal to 11, and tau I equal to 20. So suffice to say, this is the PI controller because you only have 2 parameters. So in the PI controller, you have the GC equal to Kc in bracket 1 plus 1 over tau IS. So based on this example, it looks like you will employ the PI controller. So in this case, we take a look one by one the figure, what is represented by the best controller setting. The best controller setting means which setting can be used to maintain the process at desired set point value. We want to ensure our response as smooth as possible. And we also want our response become faster, become quicker to reach the set point and maintain. However, sometimes when we try to assume some value, it will lead to the different profile. So for example, we start with the figure number 1 here. So in this figure number 1, the Kc equal to 5, tau I equal to 5. So let's say in this case, the set point that we want to maintain is at 0. So this is our set point at 0 value. So when we use the Kc equal to 5, tau I equal to 5, you can see the process is oscillating. So here the pattern is oscillating. You have the oscillation pattern. And the rate of oscillation is getting larger as the time is increased. So this leads to the unstable response. So when we take a look, you have the oscillation pattern and the rate of oscillation is getting larger as the time is increased. When it is getting larger, then it will lead to the unstable. Unstable means your process never reach steady state condition. So you can see the pattern is getting larger, larger and larger. So it's no way, although you increase the time, in the end, you will not get the ability to reach the set point or the steady state condition. So what happened if we try to increase the tau I value? So originally in the graph number 1, you have Kc equal to 5 and tau I equal to 5. Now we fix the value of Kc equal to 5, but we change the integral time constant from 5 to 11. So what you can see here, the process right now can be maintained at the desired set point. So you can see after the time equal to 100 to 150 in the graph number 2. So this is what we call it able to maintain. Meaning that the process is reaching the set point value, which is at 0 for this part. However, if we take a look, in this case, you have the oscillation in the beginning of the response, where you have this kind, like the second order under dam. You have the overshoot. And the process is also has the oscillating pattern before it is maintained. So two main findings can be interpreted from this graph. First, by increasing the tau I value from 5 to 11, you able to eliminate oscillation on the whole. However, there are still oscillation pattern in the beginning. When we able to eliminate the oscillation pattern, then this means in the end, for graph number 2, you will have a stable response. So this is considered the stable response. Only can we eliminate the oscillation in the beginning. So what happened next is we try to increase the tau I value from 11. Now it's become 20. So for this part, we can say that as shown in the graph number 3, the oscillation has been eliminated. But still, in this case, you have the overshoot. So the peak over here represent the overshoot, where the overshoot indicate that you have the peak. The peak where in the peak represent how far it is deviate from your target value. Based on the increment of the integral time constant, we can see that the process becomes slower. So after it able to eliminate the overshoot, you can see here is the value tends to have a slow response to reach the 0 point. So this is the consequence that we need to understand. Sometimes there is no unique value for controlling the chemical process. So what we need to do is to try and error. We need to understand first the dynamic of your chemical response, and from there we adjust step by step. For this case, you can see from the oscillation, when we increase the tau I, the oscillatory response has been eliminated by the end of the operation. So next we go for the figure number 4. In the figure number 4 now, we use the tau I equal to 5, but we decrease the value from Kc equal to 5 into Kc equal to 3. So by decreasing the controller gain, we can see the oscillation has been eliminated or has been reduced. But still, you can have the oscillation here. Only in this case, although you have the oscillation in the end of the graph number 4, but almost maintained. So this means it just required longer time to become steady. So what we can do, in this case, we go for the tau I equal to 11 as shown in the graph number 5. So for this part, when we take a look, when you use the Kc equal to 3, tau I equal to 11, you have a smooth response from 50 to 150. This means your response is smooth, is able to maintain, and without oscillation anymore. The only problem is the peak here. So this is the thing that is can be further improved or not. But in overall, we can say this is the good response. There is no oscillation anymore, and your process quickly reach the steady state condition. So we take a look on the graph number 6. On the number 6 here, still you able to eliminate the response, the oscillatory pattern. Only in this case, you can see the response is lower. After it reach the highest point, then it slowly decrease to the final value, which is at 0. Still, in this case, we can see it is not steadily maintained yet because you have a slow decrement. So this is what happened when you have the Kc equal to 3 and the tau I equal to 20. This means when you increase the integral time constant to large, your response become slower. And then we take a look on the Kc equal to 1 and tau I equal to 5 as shown in the graph number 7. So for this part, you can see when we fix the tau I 5 value, we decrease the Kc from 5 to 3 to 1, your oscillatory response is gone. It's slowly eliminated. Only in this case, you can see the response getting slower. Still, you have the oscillatory. Only in this part, the slow oscillation has been obtained by decreasing Kc value. In the graph number 8, when we increase the tau I, you're able to eliminate the oscillatory. There is no oscillatory here. What you can have is the overshoot. So this is known as the overshoot when you have the peak. And lastly, in the graph number 9, when we increase the tau I, you can see the response is getting slower. So this is what happened when we try to adjust the Kc and tau I value. So this indicates that the controller parameter affecting our overall closed loop performance. So that's why we cannot simply use any arbitrary value So let's say we try to assume we see that the response is not okay, we cannot conclude it is not okay. Let's say you want to use the PI controller. In the PI controller features, it's able to eliminate the offset. But how good it is, we need to put the value and see how the response. And based on the response, we need to do the further adjustment by increasing or decreasing your controller parameter and check how your behavior can be further improved. So based on this, you have 9 graphs. The best condition, what we can say for this part is the number 5. So number 5 in this case is the best response among 9. Although here we can say that you have the peak, but maybe it is unavoidable. But we can conclude after time equal to 50, your response becomes smooth, become steady. So this is one of the features of your best controller setting. So in the end, how we can judge our response is okay or not? Normally, we need to have the characteristic. So this is the desirable controller feature that can be used as guideline for deciding our best controller, where first, the closed loop system must be stable. So here, this is the first features, first characteristic or first guideline. Your response must become stable. When it becomes stable, then it is need to be maintained at the desired set point. And the second is the quick response. We want to have the fast response of our process. We don't want it become slow. So because here it will lose sometimes when the process is slow, this means you will require a lot of time to ensure the process satisfy the given operating range. And of course, normally based on our case, we have the set point changes and disturbance changes. So this to ensure when you try to do the calculation, normally you will calculate two offset, one for the set point changes and one for the disturbance changes. In every chemical process, we involve both. Set point means if we change the set point, is it your process able to maintain or not? Let's say first, initially for temperature control, you want to maintain the process at temperature 300. T equal to 300 degrees Celsius. So you try to observe, okay, then let's say you able to maintain at 300. Then you change to 350, see how your controller respond. So if it's able to maintain at the different set point, then we can say it has the good set point tracking. The same goes with the adequate disturbance rejection. Normally, you have the GP and the GD, the process transfer function and the disturbance transfer function. In every cases, we have the disturbance transfer function where the disturbance sometimes will influence our total response. So we need to ensure our controller able to reject any kind of disturbance. And then, of course, the steady state error is eliminated. Steady state error is eliminated means your offset becomes 0. And avoid excessive controller action. Sometimes your controller action tends to be aggressive. When you have aggressive controller, it may lead to the overshoot or the oscillatory response. And then number 7 and number 8 is based on the operating condition and the sensitivity of the model. So this is the thing, the features in order to ensure you have the controller, good controller setting. So in this case, of course, this is to summarize two important objective in the control application: the performance and the robustness. The performance here, this means you have the rapid, this means a quick response, and smooth. Smooth, that means without the oscillation. Or if you have the oscillation, if it is unavoidable, then we need to have minimum oscillation in our case. And the robustness in this control application, that means it can be performed at the wide range of conditions. And this wide range means you have a different set point, different disturbance, still your controller able to maintain its process. So we take a look the controller design and tuning. So in this case, how to calculate the controller parameter. So let me remind you again. You have the GC. GC, you have the P controller, PI controller, PID controller. Where in this case, the P normally is the GC equal to KC. PI GC equal to KC 1 plus 1 over tau IS. And lastly, the PID GC equal to KC 1 plus 1 tau IS plus tau DS. So for what is mean by PID controller design is we want to find using certain method how to get the KC value, how to get the tau I value, and how to get the tau D value, where the KC represent the controller gain, tau I represent the integral time constant, and the tau D referring to the derivative time constant. So we take a look on how direct synthesis method and internal model control can be used to calculate those values. Firstly is the direct synthesis method, where in this case, it is use the first order plus time delay model. So this means whatever the value that you have, you need to construct first order plus time delay model, where the first time delay model, you have the following form. So this is the standard form of the first order plus time delay. So that means whatever transfer function you have, you need to construct into the first order plus time delay. So for direct synthesis method, it employs the first order plus time delay model to calculate the PI controller. So the where your GC equal to KC 1 plus 1 tau IS. So based on the first order, you have the K, the gain, the tau, the time constant, and the theta, the time delay. So all of information of this will be used in the following formula. So for direct synthesis using the PI controller, this is the formula that need to be used, where from the formula, the Kc equal to 1 over K, multiply with the tau over theta plus tau C. So here the K, the theta, the tau is obtained from the first order plus time delay. And the tau C is the constant tau. So this one can be used in the further guideline. How to get it is based on the following guideline. Either we can use the Rivera et al. 1986, where it indicates that tau C greater than theta, greater than tau C divided by theta greater than 0.8, and tau C greater than 0.1 tau. So this is according to Rivera et al. How to find the tau C. And another guideline is based on the Chern and Fluhauf 1990, where it indicates that the tau C must be between tau and theta. And lastly, by Skojestad 2003, the simple one is assume the tau C must be equivalent with your time delay value. So why you have a different guideline? Because in this case, different application require different tau C value. How to know which one is the best? No way. Unless you calculate, you test in the closed loop. By calculating this value alone cannot be used as criteria for selecting which one is the best. Normally, what is the process control engineer do is use any guideline and then see, calculate the controller parameter using any method, and lastly, testing in the closed loop simulation. That's how the practical way to do it. So here the tau C can be obtained or can be estimated by any of these guidelines. For the test, or for the final examination, or for the project later on, it will depends on what method will be decided. If no method for choosing the tau C is given, then you can use any of these guidelines. Although it can be said that normally the simple guideline or widely used is based on the number 3. Number 3, tau C equal to theta. So because this one is the simple one, it does not require any calculation. So we just take the time delay value and this can be assumed as your tau C. So for the tau C alone, you can calculate, you can insert it in the equation and use to calculate the Kc value. And lastly, the tau I equal to tau. So here the time constant from the time delay, from the first order plus time delay model is directly used as your integral time constant. So for this part, you can see that the PI controller can be calculated using the following formula using direct synthesis method. How about the PID? So for the PID, in the direct synthesis, it used the following equation. So for the PID, you require 3 terms. GC equal to KC, 1 plus 1 over tau I plus tau D. So you have 3 controller parameter. So for this part, in the direct synthesis method, it used the second order plus time delay model. Where in the second order plus time delay, you have the K exponent negative theta S over tau I S plus 1, tau 2 S plus 1. So once you obtain this model, then you can further use in the given formula how to calculate the Kc, the tau I, and the tau D. So for this part, I'm not too worried because the formula is readily available. You can refer to your textbook and it is straightforward. Once you obtain the first or second order plus time delay model, then the calculation is very straightforward. There is no trick on this case. Same goes with the tau C. So for the second order plus time delay, you have the tau C here. So the tau C, you can use the given guideline. So this one is also straightforward. So that is the formula for calculating controller parameter in the case in the method of direct synthesis. Another method that can be used is what we call it internal model control, where here this internal model control is based on the process model assumption. Again, this one you can refer to your textbook where there are different cases how to calculate the controller parameter. And this case, if you take a look, you have the case A, B, C, D, E, F, G, H. In the textbook, I think you have some until K or L cases. Depends on the type of the model. So normally what we are interested is the type G, case G and H, where you can see this is the first order plus time delay model. And this is the formula for calculating the K, C, and the tau I. And the H, there are another formula where the different formula will be used. So what is the difference between G and H is normally the G is applicable for PI control. So if we want to control using type of PI, then you use case G. For case H, normally it represent the PID. That's why you have the three terms for case H. So this means once you obtain the first order plus time delay, we will use the following formula. Case G for PI, case H for the PID. How about P controller? So how to calculate the P controller? In this case, you can use the case G. So the G itself can be used for the P or PI control. So in the P control, you have the only case C. So that means you don't need to calculate the tau I. It's like that. The similar guideline will be used for determining the tau C as shown in this slide. So you can choose either using the Rivera et al., Chen and Fulhoff, or the Skojestad method. And another method that can be used is based on the error according to the time domain. So for this part, we have several methods to calculate the controller tuning method, either using the integral square error, absolute value error, or the time weighted error, time weighted absolute error, ITAE. So for this part, another method is the ITAE, where the ITAE stands for the integral time weighted absolute error. So this is the method based on the first order plus time delay. So this means whatever you do, you need to develop the first order plus time delay model from your transfer function. So in this case, you have two inputs, either the load or the set point. The load here sometimes represent what we call it disturbance. So if you recall, there are two changes, the set point changes and the disturbance changes. So here you have the disturbance and the set point. The disturbance also is known as the load input changes. So for this design relationship, we have the PI and PID, and you have the mode P, I, PID, PI and D. So where the P represent the proportional, I integral, and D derivative. So in this case, you have the A and B. A and B is the coefficient. For example, here, how to use it, we can refer to the side note in this table, where the design relation is based on the Y A theta over tau power of B, where the Y can be represented as the YKKC for proportional mode, tau over tau I for integral mode, and lastly, tau D over tau for derivative mode. So in this case, A and B coefficient is depending on the type of your controller. Either you want to calculate for the KC, tau I, or the tau D. The value of A and B are different. So this is the sum of the formula. So don't worry about that. Maybe later on we will take a look on the exercise on how to employ this formula. Here we just go through the formula, the briefing of your available tuning method. So others PID controller tuning. You may ask why we have so many controller tuning. How many is actually available in the open sources? There are so many controller tuning. Because this one is based on the different method. It's not that because here we just need to have a clear idea. Sometimes in every chemical process have a different characteristic, different dynamic. So we don't have any unique tuning method that can be applied for wide range of operation. Sometimes in this process, specific tuning method is used. Let's say for maintaining the temperature control in the chemical process. Maybe you can use the direct synthesis method. But if you want to control the flow or the level, maybe you need another method. There is no widely accepted method that can be applied for wide range condition. That's why in this case, you can see various formula of PID controller method. So in another way this is the Ziegler nickel and Cohen-Kuhn. Actually, this is the beginning of the controller tuning method. So these two people, Ziegler nickel and Cohen-Kuhn, created this formula to calculate the controller parameter, where here you have the Ziegler nickel that can be worked on the proportional integral and proportional integral derivative. Another formula for that can be used. Although it can be said that all of it is based on the first order plus time delay model, where you need to have the GS equal to K exponent negative theta S over tau S plus 1. So this is the requirement. We need to develop the first order plus time delay. Once you have this model, then afterward it is a straightforward to use it to calculate the Kc, tau I or the tau D. So that is the phi of the formula, which consists of the direct synthesis, internal model control, integral time weighted absolute error, Ziegler nickel, and Cohen-Kuhn. So in this case, you have the formula. Next step is how to apply this formula. So any question on that? Okay, we take a break before we continue. In this case, I'm not too worried because this one is the simple. This is, I think, the simple part of the subject. You just apply the formula. So in the second part of our class today, we will have the tutorial regarding this method. So we take a break and we continue around 1 o'clock. Yeah, doctor. Okay, let's continue on the second part of our class, which is the exercise relating to the controller tuning method. So in this case, please refer to the given attachment, the exercise. So for this part, we have a standard closed loop block diagram which has the following transfer function. So here we have the GP, the GM, the GV. So you have the GP 1 over 5s plus 1, the GM 5 over 10s plus 1, and the GV 2 over 3s plus 1. And then in this case, if proportional integral derivative PID control is applied, then you have the following formula. GC equal to KC in bracket 1 plus 1 over tau IS plus tau DS. So based on this, how we can obtain the value of the KC, the tau I, and the tau D. So this is the question actually. So in this case, we require the first order plus time delay model or second order plus time delay model. So how to generate, to construct the first order or second order plus time delay model? So normally, in this case, if we try to refer back in based on our block diagram. So let's recall. So you have the KM. And then the comparator, you have the GC. You have the GV. You have the GP. And then you have the GD coming to here. And then you have the GM. Go back to the process. So in this case, you have the block diagram where you have the Y prime SP, S. So the thing that we want to obtain is your GC. Your GC. So for this case, the question asks you to use PID controller as your GC. In the PID controller, you can see in the transfer function, you don't know the value of the KC, tau I, and tau D. So for this part, we can use different controller tuning method to calculate the controller parameter. Before we can employ any controller tuning method, we need to construct the first or second order plus time delay model. So for this part, normally, if you want to calculate the GC, this one is based on the closed loop performance. So the closed loop is here. This is the loop. So in the closed loop, it involves the GC, the GV, the GP, and the GM. So since here, the one that we want to calculate is the GC. So this means in order to obtain the correct information about GC, we need to use the transfer function involving the GV, the GP, and the GM. Again, I repeat, because this one is not clearly stated in your textbook, either in the third or fourth edition. We want to calculate the controller parameter, GC. The controller transfer function in this case is your GC. So for obtaining the correct value or the accurate value for our GC, we need the combination of GC, of the GV, the valve, process transfer function, GP, and the measurement transfer function. Why we need all of these three? It is because this is based on your loop. Where in the loop, you have 4 transfer functions, GC, GV, GP, GM. So by excluding the GC, because the GC is the one that we want to calculate, so we need to have combination transfer function for valve, process, and measurement. So here the G equal to GV multiplied by GP multiplied by GM. So here that's why you have the information relating to the GV and GP and GM, where your GV is 2 over 3S plus 1 multiply with the GP 1 over 5S plus 1 multiply with the GM 5 over 10S plus 1. So in this case, we have the GP, GV, and GM. So when we try to simplify it, it becomes 2 multiplied by 5 is 10. Then we rearrange the denominator 3S plus 1, 5S plus 1, 10S plus 1. Alright. So this represent, if you take a look, you have 3 different tau in your denominator. So this means if we take a look, this can be represented as your third order. Third order. Because you have 3S plus 1, 5S plus 1, 10S plus 1. If you expand it, it becomes S power of 3. That's why it is called as a third order. So our objective is what we want to obtain. How from the third order can be transformed into first order plus time delay. So this is the main thing where originally we have G over 10, 3S plus 1, 5S plus 1, and 10S plus 1. We want to convert into K exponent negative theta S over tau S plus 1. So this is the standard form of your first order plus time delay. So if you can take, you can see here originally we have third order. We want to make sure it become the first order. And then we need to include the time delay. So this can be done by using Taylor series expansion. Taylor series expansion, where you have the equation exponent negative theta S equivalent with the 1 over 1 plus theta S as shown in the equation 558, page 86 in the third edition textbook. So this is by using the Taylor series, we can reduce our equation into the first order. The problem here, we have 3 different tau. So for this part, this is, let's say this one, tau 1 equal to 3, tau 1 equal to 5, and tau 2 equal to 5, tau 3 equal to 10. We have 3 different tau. Which one should be left behind and which one should be located as your time delay? So normally in this case, the largest time constant should be left behind. Among these 3, you have tau 1 equal to 3, tau 2 equal to 5, tau 3 equal to 10, where the largest is tau 3 equal to 10. So this will remain as your time constant. And the tau 1, tau 3, tau 1 equal to 5 will become your time delay. It's like that. So based on this, your equation should become 10 exponent negative 8s divided by 10s plus 1. So this is your first order plus time delay from the third order transfer function. Again, here I repeat the objective now. Based on the G equal to GP, GV, GM, you have the third order. The question here, in order to use the tuning method, it is need to be in the form of the first order plus time delay. That's why you require K exponent negative theta S over tau S plus 1. Because that is the standard form of the first order plus time delay. So the question is how to convert the third order into the first order plus time delay. In order to do so, you need the Taylor series expansion. Where the Taylor series expansion, the time constant can be converted into your time delay. The problem here, you have 3 time constant. Tau 1 equal to 3, tau 2 equal to 5, tau 3 equal to 10. You have 3 time constant. Which one should be selected as your time constant and which one should be selected as your time delay? So for the first order plus time delay, you require only one, tau S plus 1 on the denominator. So you need to select the largest time constant, value to be used as your time constant. Why we need to select the largest one? The largest time constant normally affecting more on your process compared to the smaller value of your time constant. Among these 3, you have tau 3 equal to 3, 5 and 10. So 10 is the largest time constant and it should be remain as your time constant in the first order plus time delay model. So that's why 10 is left behind in the denominator. And since you have tau I equal to 3 and tau 2 equal to 5, what we are going to do? It become the time delay. So 3 plus 5 is equal to 8. So this one, based on the Taylor series, from the denominator, it become the time delay. That's why you get G equal to 10 exponent negative 8s over 10s plus 1. Any question?
So, sir, the tau become the largest value, right? 10. And the theta is the addition of a smallest value. So, what's the value of k, sir? Why k become 10?
In here, the K is the represent your gain. So here you have 10 as your K. And this one is also K. So you just straightforward. It does not involve any modification.
Oh, all right, sir, got it.
So because the T here is your gain. So if we try to compare side by side, the gain is not changing. Only the theta and the tau will be changed because you have more than one time constant. So for this part, the K normally you can use as it is. So this is the first order plus time delay model. And how we can obtain second order plus time delay. So for the second order plus time delay, SOPTD, second order plus time delay, you have the following model. K exponent negative theta S over tau 1S plus 1, tau 2S plus 1. So the difference is you have additional tau in the second order because it is not a second order. So you have 2 tau in the denominator. So how to change the third order into the second order plus time delay? Similar approach can be used where here the K is also 10 because it's not changing. And then for the second order, you have 2 tau here. tau 1 S plus 1, tau 2 S plus 1. This means, compared to the third order, you have 3. Tau 1 equal to 3, tau 2 equal to 5, tau 3 equal to 10. Similarly, in the first order, plus time delay, you require the largest time constant. So for this part, since you need 2 tau, so you need to select the largest and the second largest time constant. So the largest and second largest is the tau 2 equal to 5 and tau 3 equal to 10. So that one will be selected as your time constant for the second order plus time delay. 5S plus 1, 10S plus 1. And tau I equal to 3, what happened? It become your time delay. It's like that. So this is the first order plus time delay and the second order plus time delay for the given problem. Any question? All right. So now we obtain the first order and second order. So this is our first order model, second order model. So we can move to, so we complete the A equation, develop first and second order. So now we back to the objective. We want to calculate the controller parameter. So this is the thing that we want to calculate. Right. This one, for this method here, determine the PID controller for this. So we need to calculate the Kc, tau I, and tau D. So here we use the direct synthesis method. So if we go back to our slide before. Okay, this is our slide. So here we use the direct synthesis method. Direct synthesis method, you have two, first order plus time delay. So this one, for the first order plus time delay model, using direct synthesis is only applicable for PI. So we cannot use it. So for the PID, so this is the formula. Then it require the second order plus time delay model. So for this part, let me copy the equation. So this is the equation for calculating direct synthesis, for calculating controller parameter using direct synthesis method. So here the problem is the tau C. Tau C, as shown in this one, let's say we use the Skojestad problem. This tau C equal to theta because this one is the simple one. So I just copy paste here for understanding. So now, in this case, we have the second order plus time delay, which is this one, 10 exponent negative 30s, 3s. So based on the second order plus time delay, we have the GS equal to 10 exponent 3 negative 3s over 5s plus 1, 10s plus 1. So in this case, based on our model, the K equal to 10. The tau 1 equal to 5. Tau 2 equal to 10. And the theta equal to 3. So for this part, it's okay if you change tau 1 equal to 10, tau 2 equal to 5. It's okay, no problem. Because both will contribute the same answer later. So it does not matter if you change the arrangement of your tau. So for this part, I think this one is straightforward. Only here the tau C. Tau C equal to theta. So for this part, tau C equal to 3. So this is the assumption used by using Skojestad guideline. So the next step is the Kc equal to 1 over K. So here the K should be 10 multiply with the tau 1 plus tau 2. 5 plus 10. Tau C plus theta. Tau C is 3 plus 3. So this equation coming from here. So we use the following formula. We replace the K, the tau 1, the tau 2, tau C, and theta. So you can obtain the value of your Kc, which is, calculate it.
One over four.
1 over 4. So we complete the Kc value. Now we go for the tau I. Tau I equal to tau 1 plus tau 2. So this one, the tau 1 is 10 plus 5, 15. So we complete the tau I, and lastly the tau D. The tau D equal to tau 1, tau 2 divided by tau 1 plus tau 2 equal to tau 1 is 5, tau 2 is 10. Tau 1, 5 plus 10. So what is the value?
3.333.
All right, thank you. So this is the controller parameter value using direct synthesis method. Where the Kc is 0.25, tau I is equal to 15, and the tau D equal to 3.33. So here why we use the second order in this case, because the formula for direct synthesis indicating second order could be used for the PID controller. So we move to the next method. Before that, any question? So in this case, we use the internal model control. So we take a look on the formula, the next method. So this is your formula. All right. So here the internal model control, in this case, we can use either case G or the case H. Only in this case, the case H represent the first order plus time delay model, and you can calculate it for the PID. So it involves three different terms. For the case G, is only applicable for the P or PI control. Case H is require the PID control. Since the question asks you to determine the PID controller setting, then we use case H. So for this part, it just require the first order plus time delay model. So for this part, this is our first order plus time delay where the G equal to 10 exponent negative 8s 10s plus 1. So for this, where based on this equation, you have 10 time delay and the time constant. So this represent your K, your theta, and your tau, where the tau C equal to theta equal to 8. So this is the description of each coefficient involved. And then here we want to calculate the Kc. So the Kc here, you can take a look. This one is you have Kck. So this means how to construct the correct formula. Kck equal to this one. Tau plus theta over 2 divided by tau C plus theta over 2. Like that. So for this part, we know that the K is 10. 10 Kc equal to tau is 10 plus theta over 2. Theta is 8 over 2 divided by tau C. Tau C is 8 plus 8 over 2, which is this one, 10 Kc equal to 10 plus 4, 14 divided by 8 plus 4, 12. So Kc equal to 0.1167. So this is the Kc value for using internal model control, case H. And for the tau I, this is your tau I. So tau I equal to this one, tau plus theta over 2. So here the tau I equal to tau is 10. Theta is 8 divided by 2. So you get 14. And lastly, the tau D. So here the tau D equal to tau theta divided by 2 tau plus theta. So the tau D equal to tau is 10, theta is 8. 2 multiplied by 10 plus 8. So tau D equal to 2.86. So this one I think is very straightforward because you have the formula, you just insert the required value inside the formula and you obtain the final controller parameter value either for the KC, the tau I or the tau D. Any question? Okay, since there is no question, then I think you can finish the rest of the exercise. So here I already show you the direct synthesis and internal model control. So you for the further exercise, you can complete the number 3, number 4, and number 5. So you just use the formula given and calculate the value for your practice. So now I would like to shift our attention. So by completing the controller tuning method, so that means we reach the end of chapter 3. So we already complete chapter 3 for this subject, where it covers mainly on the overall closed-loop transfer function, offset calculation, stability analysis, and the controller tuning. So this chapter represents one assessment, which is known as the project. So for this part, you can refer to the Google Classroom. In the Google Classroom, you click the project process control and dynamics. So this has been assigned to everyone. You can have the project PCD, BKF3413. So here, let's say you can refer to this project PCD. So it's involved the feedback and PID tuning. So here, the objective is to develop first order plus time delay model, perform the stability analysis, and then simulate or calculate firstly the controller tuning method and lastly the simulation. So this project represents 15% and the submission deadline will be 30th of June, 1 month from today. So in this project will be conducted as a group and the maximum number of group will be 6. Maximum member in one group will be 6. So you can choose your own member. Because here I would like you to have the good mark, so you choose your own member. So maximum number is 6 and the deadline will be 1 month from today. And this is the description. You can take a look later on. The only thing that I want you to focus here, we have the figure 2 and figure 3. So this represents the step change of the input over the output. Why you have the two graphs, that means it represents one for the process transfer function and the second one represents the disturbance transfer function. So you need to obtain the GP and the GD from the given process. So here the task for the project, once you obtain that, the first order, you can refer to the task for project A, in this case, you need to assume the time delay between 0.5 to 5 minutes. So this one, I let for you to choose it as long as it satisfies the time delay here. Then you need to evaluate the stability of closed loop system using rule stability criterion using P, PI, and PID, where the assumption used is GM equal to 1 and GV equal to 1 over S plus 1. And then for the C, D, and E, calculate controller tuning parameter using the direct synthesis, internal model control, and the ITAE. So this has been covered by today. So that's why I'm giving this project starting from today class. So you have the CDE, and then lastly, you need to develop the closed loop control flowsheet in Simulink available in MATLAB software. So for this part, you require MATLAB software to demonstrate the simulation work. So how to download the MATLAB software? You go to the Google MATLAB free download. Then you can download it. If let's say your computer not supporting not supporting the given software, you can come to our PCI lab. You can come to our chemical lab to where we have the computer lab in the faculty. So you can use the computer if you are available in UMP. Since this one is carried on the basis of the grouping, so I hope there will be no problem. Make sure at least one of two members able to simulate the file. So for this part, I let you to refer the transfer function in Simulink in YouTube. There are a lot of video involving how to simulate the file in the Simulink. So I hope you can search it. And then G, you need to perform the closed loop simulation in Simulink. So once you calculate the controller parameter, you determine the simulation. You perform the simulation to determine the best controller performance. And of course, lastly, once you obtain the result, you can discuss each simulation results based on the theoretical, justify which controller gives the best performance. So this is the task that needs to be completed for project, and it represents 15%. And all of the item must be compiled in the report, and you need to use Microsoft Word. I suggest for you to use Microsoft Word as a medium to prepare the report, and the item must be include the introduction, the literature, methodology, result discussion based on the item A to H. So the report must be typed using Times New Roman. The size of the font is 12 and 1.5 spacing. All of the calculation must be included in your report as together with the screenshot of your simulation results. And you can refer to our project report rubric for further explanation regarding what item that will be assessed. So this document is referring to the rubric, and the distribution of the mark is given. So make sure you complete all of the document, all of the tasks, and check in the rubric what is the necessary item that needs to be included in your report. So here the report total mark, it will be 100 and it will be converted into 15%. Okay, that is the project assessment for this semester. Any question relating to the project assessment? Okay. No question. Then I assume everything is in order. So this is the end of week 12. So good luck for the completing the project. And next week we will continue with the new topic, the last topic for this subject, which is the frequency analysis. Of course, feel free to contact me for further question. If you have a further question relating to this topic. And I think that's all for today. And thank you again for your cooperation and the response. So that's all for today. Class is dismissed and have a good lunch. Thank you.
Thank you, Doctor.
Thank you, Doctor.